My friends in like electrical engineering and computer science, computer engineering, they were all very comfortable with digital signal processing. They took a course in that. They understood convolution. All that was very simple. Whereas some of us in aerospace, mechanical, civil, we don't get to see any of that. And I think that's a big problem. Nowadays, with everything we do being on a computer, really everything we do is sampled. We need to understand signal processing. Everything, data we acquire is on a computer. Analysis we perform are digitized. So a course like that should be a requirement, absolutely. These are the topics: mathematical preliminaries, unsteady aero, aeroelasticity, ASC, reduced order models, and discussion. All right? But again, I hope you jump in at any point that you think is necessary. Classification of systems. This is not something you'll see in most textbooks on elasticity. I don't think it shows up in any textbooks, or unsteady aero. But to me, it's essential for you to understand the nature of a system before you attempt to model it. Most of what you're going to be doing throughout your career is modeling or analyzing or trying to understand some physics. And you come up with an approximation to those physics. Okay? If you don't understand the nature of the physics you're trying to model, you're not going to develop a good, sound mathematical model of those physics. So you have to understand what it is you're talking about. And there's a language, there's a certain nomenclature, and this is what I like to share with everybody. So here's some references from some classic references, excellent textbooks. Autonomous second-order nonlinear systems. Right now, your understanding of that term may or may not be clear, okay? But I guarantee you, by the end of this morning's discussions, it will be clear to you. You will know exactly what that means. We shall restrict our attention to second-order autonomous systems where time does not enter explicitly into the equation of motion. This, of course, precludes time-dependent forcing functions. Okay? Now, with regards to concepts like unit step and unit impulse functions, there are comments in textbooks that say, whereas the unit step function is well defined, the unit impulse function, mathematically speaking, is not. Okay? Once we're done talking about all this stuff, if you see these again, you'll be like, wait a minute, no, those can't be right. Okay? So what do they mean? How do we understand these concepts, and how do they apply to real-world systems? This is one way that I've put together as a way to classify systems so you understand kind of where they fit. I don't see a laser. I'll get it at the break. By the way, we're going to have a break about every hour for about a 5-minute break. So don't worry, I'm not going to keep you here for 3 hours nonstop. There's classes of systems like time invariant and time varying. How many of you are familiar with the term time invariant? Raise your hands. Okay. And now, there's also misconceptions about that, so we want to be clear. I will talk to you about mathematically what it means, as well as physically what it means. Those are important concepts. You can have time invariant or time varying, and within that scope, it can be linear or nonlinear. It can have zero memory or memory. Okay. I won't go into it right now, but you see that this is linear, but y equals mx plus b, you say, wait, that's the equation of a line. But if you try to apply superposition to that, it's actually a nonlinear equation. And that blows a lot of people away. But we'll see what I mean by that. So linear, nonlinear. All of you have been exposed to linearity and nonlinearity, but can you classify? Can you tell me mathematically what it is? Or experimentally, can you tell me what it is? Can you go into a lab? If you have a machine, it's got 3 levers and 1 response. Can you tell me if that machine is linear or not? How would you do that? What experiment would you perform? Okay, well, this is one way to think of that. So a linear system, superposition is the whole key. What that means is that if I have, and think of S as the system, and all these multiple inputs, right? Superposition says that if I excite the system with a whole series of inputs simultaneously, that is the exact same thing as if I excite each input separately and add them up. That's what superposition means, right? So let's talk about that machine in the lab with the 3 levers and 1 output. How would you prove to me that if I ask you, okay, your assignment is, I need to know this machine is linear or nonlinear. How would you do that? You push lever 1, you measure it. You push lever 2, you measure it. You push lever 3, you measure it. You save those 3 measurements. Now you push all 3 levers at the same time, and you measure that response. Add those 3 previous ones. If those are exactly equal to the one you just did, this is a linear box. It's a linear machine. If that's not the case, it's nonlinear. Okay? Notice the terms we use in mathematics. Things are either linear or they're what? Not linear. Because it's much easier to put everything into this big box of linearity. I know. Linearity, I understand. Linearity is great. It's simple. I can scale it. I can multiply it. If I double the input, I double the output. It's simple. Nonlinearity, not so simple. So things are either linear or they don't belong to that set. But the reality is most physics, most real world, is actually nonlinear. Linearity is an incredibly unique exception that we've created for ourselves in order for us to be able to mathematically deal with the modeling. Okay? Any questions? Yeah?
So does the output function have to be quantifiable for it to be linear?
I'm sorry, I couldn't hear you.
Does the function output have to be quantifiable for it to be linear or not?
Quantifiable, I'm assuming you mean measurable? Well, yes. Yes, you have to be able to use that equal sign, right? If I have an output, I can't quantify it, then I can't relate it. So yeah, you have to be able to measure it in some sense. Now there's uncertainties, there's measurement errors, all those things. But this is the theoretical description of that. Does that answer your question? If some function does what?
If with a lever, suppose those levers actually perform some action, what does that even mean to add?
Right. If I push on the lever, this machine, that's an input. The lever is an input. So when I push on that lever, out of 3 levers, only lever 1, I get some response from that machine. The machine does something because of that. And I save that response. That's what I mean. Does that make sense? Okay. For nonlinear systems, superposition fails, and it fails quite drastically. Here we have y equals x squared. It's nonlinear because it's quadratic. Assume the input is x, okay, and the output is y. If you use cosine omega 0 t, the output is actually 1/2 plus 1/2 cosine 2 omega 0 t. Here is a hallmark of nonlinearity. A nonlinear system or a nonlinear process can and often does generate a bias which was not there as part of the input or a new frequency which was not part of the input. Very important. A linear system will never, ever, ever create a new frequency. So if I have a linear system and I input a 1 hertz, a 5 hertz, and a 12 hertz signal into that linear system, the amplitudes and the phases might be different, but the output frequencies are going to be 1, 5, and 12. No doubt about it. Nothing new, nothing different. Guaranteed. That's another way for you to determine if your experiment or your analysis or your computations, if they're linear or nonlinear. Are any new frequencies being created? If you, in fact, you apply a 1, 5, and a 12, and output I get 1, 5, 12, 10, 15, 20, 24, I'm getting multiples of my input frequencies. That's nonlinear. That's guaranteed to be nonlinear. We call those harmonics, okay? So that's guaranteed, right? And here's why superposition doesn't work for a nonlinear system. Remember, superposition means apply inputs simultaneously should be the same as applying the inputs separately. But if I apply inputs simultaneously for squared, notice I get this term, the cross term. If I apply them separately, I only get those two. So for a nonlinear system, when you apply the inputs separately, you will never get the cross term. So that's why superposition fails and quite dramatically for nonlinear systems. Okay, does that make sense? So this is what I was just talking about. Linear systems cannot create new frequencies that are not present in the input. Whatever the input is, the F1 is still going to be an F1. A2 could be different from A1. Phi2 could be different from Phi1, but F1 will never, ever be different. That's guaranteed. Okay. Nonlinear system, however, you can get multiples of the input frequency, F1, F2, and so on. Those are harmonics, which are multiples. And you get subharmonics, which are fractional multiples of the input or exciting frequencies. Okay. How many of you have seen this before? Raise your hands. Okay. Now, this is a classic term that causes significant amount of confusion. I've come across references, texts, where it's not described properly, and just because of the term, language is a very interesting concept, and you have to be careful with how the language is used to make sure you understand it. Now, the word time invariant makes you think that nothing changes with time, and that's partly true, but you got to be careful. So it doesn't mean that it's steady. Now, a time invariant system actually also means shift invariant, and you'll see why that's a more valuable name. But if I give you an equation, an ordinary differential equation, or a partial differential equation, or any kind of equation, which of course has derivatives. So right away, notice, it has derivatives. If it has derivatives, it can't be steady state. So time is an implicit function here, but the difference is that a time varying system, time is an explicit part of the equation. Time shows up explicitly. Okay? So now, another huge misconception that I come across is that folks, in some references say, well, this is a linear system, so it's time invariant. That one's nonlinear, so it's time varying. That's totally wrong. Totally wrong. A system can be linear or nonlinear. It can be either time invariant or time varying. That's got nothing to do with it. Those are two separate types of classifications. Okay? Now, physically, what does this mean? A time invariant system, physically speaking, let's not talk about the mathematics right now. Let's talk about the physics, because this is a physically meaningful concept. It's not an abstract mathematical idea. What it means is that the time at which I apply an input does not affect the output. So, if I apply a certain input at T1, I get a response. If I apply the exact same input at a later time, T2, I still get the exact same response. That's time invariant. Think of this as, let's say you have a mass spring system in your lab. You come in at 9 in the morning, right? You have your coffee, because you got to have your coffee, first things first. You excite the mass spring system, you measure the output. Okay. You come back at 3 in the afternoon. You might have more coffee, because maybe you're hooked to coffee. I don't know. And you apply the exact same input. What do you expect to see? The exact same output, right? Why? But it doesn't mean that there's no unsteadiness. It doesn't mean that there is no function of time. It's just that the system itself, the properties of the system, are not changing with time. So that type of system is invariant to the shift. So if I shift the time at which I apply the input, it has no effect. That's known as a shift invariant system, time invariant. Now, time varying system is the opposite, or doesn't hold that. If I come into my lab and I apply an input to this system at 9 in the morning, I measure the output. If I come back later, now let's say the mass spring system, let's say the mass was actually a bucket of water, and now that bucket has a small hole. I come in at 9 in the morning, there's a certain amount of mass, I get a response, right? I come in at 3 in the afternoon, I apply the exact same input. The response is different. Why? Because there's less mass. Water has leaked out of the bucket. Okay? So, what are some examples in aerospace? Rocket is time varying, no doubt, because it's burning so much mass, so much fuel. So once it launches, right, if I apply an input 5 seconds after it launches, I measure the response. If I wait 30 seconds more, I apply the exact same input, the response is going to be different, because the mass has changed so much. That's a time varying system. Let me ask you a trick question. This one's going to be worth 50 points. Airplane. Time Time varying or time invariant? And by the way, your professors are connected online. They're keeping an eye on all of you. So, airplane, time invariant, time varying?
Time varying.
Strictly speaking, that's right. Why? Because fuel is being burned. As the plane flies, it is being burned. But if you go back to your textbooks on aerospace and aeronautics, you'll find an assumption that's made that's kind of thrown out real quickly out there. It's never really discussed clearly. That is, one is that it changes so slowly that what you do is you break it up. You break up the vehicle into empty fuel, half full fuel. So you take a time varying system and you break it up into 3 systems that are time invariant. Why? The mathematics are much simpler. It's much easier to deal with that. Okay? Does that make sense? So, time invariant, pendulum, other things, rocket, leaky mass spring system, others mentioned this already. Memory versus memory-less. This is a system or class of systems that we work with all the time, but we don't call it that. But it's good for you to know the nomenclature. It's good for you to understand the terminology, because if you're going to deal with nonlinear dynamics, this comes into play a little bit more. For example, memory is a system where future outputs are influenced by past inputs and outputs. So anytime you have an equation with derivatives or integrals or integral differential equations, by definition, that's a system with memory. Okay? So you might say, well, what's a memoryless system? Okay? Well, this equation, y equals 2x, is memoryless. It has no derivatives, it has no integrals. But what makes it memoryless? What does that mean? Well, let's say I apply these inputs, right? I apply 1, I get a 2. I apply 2, I get a 4. I apply 3, I get a 6. If I switch around the inputs, if I apply a 3 as the first input instead of 1, I still get a 6. So you see, if I apply 3 as the first or 3 as the 8th, I'm always going to get a 6. It doesn't matter what came before. It doesn't matter what comes after. It doesn't care. It doesn't know because it has no memory. Okay? With a derivative equation or an integral equation, the order of the inputs will matter, and you will get a different combination of results because each one affects the others. Okay? So that's memory and memoryless.
Well,
Yeah.
how about systems in which we sort of intentionally limit the number of derivatives? So, for example, if something depends, on a state variable, let's say the angle of attack, and the change of the rate of the angle of attack, it has some very short-term memory, but its memory doesn't go that far back. I mean, for all practical purposes, that's essentially memory. It has very little perception of the past, the way we've modeled it. Now, it may be that the system is hysteretic, and it needs a lot of memory, going back. So is there a distinction there? I mean, it comes down to sort of Taylor's assumption on the aerodynamics.
Yeah.
Do you make the aerodynamics as sort of a Taylor series?
Right.
Or not?
Right. No, that's a great question. And really, it's like everything, it's a spectrum. Memoryless are very, very clear, and that's what I'm talking about here. Those things like saturation functions, deadbeat, all those are mathematically, strictly speaking, those are memoryless functions. Now, most everything else that has derivative or whatever has a memory, and how much is something you can take advantage of. Some systems, think of a system that's lowly damped, that response is going to affect future responses for a long time. A system that's highly damped, boom, it dies out very quickly. The level of that response, and we'll talk about that later, is a measure of the memory. So systems have memory and some don't. Some have longer than others, and you can manipulate that in many ways. All right, that's a subsequent part. But memory, it's very important to know that if it's memoryless, it's got to be absolutely memoryless. Okay. This one is a little more straightforward, deterministic, stochastic. Given an input, always use the same output, repeatable. Okay, that's deterministic output. Stochastic is given input, yields a family of potential outputs. So you have the system is being defined by some probability distribution functions. So even if I apply the same input, I'm not always going to get the same output. It depends on the probability distribution function. So these are terms, again, for you to be aware of and understand so that you can at least, when you read a journal or a paper or text, these will make some sense to you, okay? And that's what I'm trying to do. Yeah.
But in the deterministic systems, there are chaotic systems.
Oh, that's...
Which are fully deterministic, but which, yes, for the same input you get the same output, but it's so sensitive to them
Yeah.
that, they seem chaotic.
Well,
I mean, they seem stochastic even though they're not.
yeah, there's a caveat you need to put here, that there are some nonlinear systems, like the logistic equation. Logistic equation, look it up at some point. It's a classic example. It's a very simple equation. It's a second order. You look at the equation, it looks totally harmless, okay? But you change this mu parameter, and depending on what you set it to, you can get chaotic response. And it's within a certain region. The interesting thing about chaos is that it's not totally random. It's not everywhere. It's chaotic within a certain range. So you know where it's going to be chaotic. You know here, 100% guaranteed, it's not. There's no chaos here. You know 100% there's no answer here. But here, it's totally chaotic, but you don't know exactly what the answer is going to be. So there are exceptions. These tend to be nonlinear systems, okay? So you're talking about linear, this makes it a little easier. But nonlinearity introduces additional complexities that can create some additional complications. So yeah, that's a valid point. Okay, any questions on this? So I won't spend a lot of time here, and I'll send these notes out. So go ahead and, when you get a chance, go ahead and classify these systems. This is a good exercise for you to look at them and ask yourself, okay, are these linear, nonlinear, time variant, time invariant, memory, memoryless, deterministic, and stochastic, okay? All right, convolution. Let's talk about that. How many of you have fond and wonderful memories of the Dirac delta function? Raise your hands. Raise your hands. You have a poster in your room of the Dirac delta function, right? It's your champion. It's your hero. It's a complicated function, right? If you remember, it's a function with an epsilon that goes to 0 as the amplitude goes to infinity, but whose integral is 1. Okay? Now, somebody tell me, what does convolution do for you? What is the point of convolution? Somebody? Anybody? Other than solving a homework problem in a class. What is the point of convolution? All right, I'm going to tell you what the whole point of convolution. Convolution is prediction. How many of you are interested in predicting the response of a system? Who isn't? And this is a question I ask a lot of times in my short courses and in my regular classes. I'll say, how many of you work with convolution every day? Raise your hands. Nobody raises their hands. Then I say, how many of you work with a system with inputs and outputs whose response you'd like to know? Everybody raises their hands. That's convolution. But that's the way I learned undergrad. It was never taught to me properly, and I'll be honest with you. I don't think it's being taught properly. I think it's being taught to be very convoluted, very complicated, but it's actually a lot simpler when you look at a digital signal processing point of view. So the whole point of convolution is that if you apply this impulse function to a continuous time, that's linear time invariant system, you get what's called H, an impulse response. All right? And so the whole point is, once you know the impulse response of a system, you know everything about that system. You can then predict the response to that system to any input. That's the power of this whole concept. But let me talk more about this. So here's how it works. If I apply this input to this continuous time function, I get H. H is called the impulse response function. If I know H for that system, I need to compute it only once for that system. I now know everything I need to know about that system. And if you come to me and say, hey, well, I want to put this system through all these different motions, through some random or arbitrary type motion, I have two options. I can take that input and apply it to the system and get a response, or since I just computed this H, I just do this integral. It's called a convolution integral. I convolve H with U, and I get Y, and it's exact. This is not approximate. For a linear system, this is exact. You get the exact same response. So, why might convolution be appealing? Well, what if computing the response Y by applying that input to the system, what if it takes 5 days? Because that LTI system is very complicated. computationally or whatever. What if it takes 5 days? Well, if I do convolution, that's simple integral. That might take 10 seconds, okay? So therein lies the benefit of convolution that's not widely disseminated or widely understood. One, it's a predictive tool. It's a way to predict something. It's a way to characterize a system. And if you have this characteristic of that system, you can use it to predict the response to that system to any other input. Any other input. Sinusoidal, step, random, anything, okay? So, what I usually tell my students is don't worry about that integral. That integral is confusing. Now, how many of you remember this thing about convolution? If you have function f and function g, and you got to do a convolution of f with g, you take one of these functions and you flip it, and then you do this weird crossing over. Anybody vaguely remember that in your worst nightmares? Yeah. It's a pretty bad nightmare. Let me just tell you that that's the way that shows up in textbooks. And I don't know why. I mean, that's the way I learned, because I never really understood it until now. But that is not the best way to teach what convolution is. It turns out there's 2 ways of doing convolution. That way, where you flip a function, that's actually the second way. It's not physical, it's not intuitive. It's just, it does provide some efficiencies that the other method does not. But I'm going to talk to you about the basic method, the one that makes physical sense. Here's how convolution works. So I have h. I computed the h before, right? I have h. Let's assume I have it. We'll talk about how you get that later. And I want to predict the response y of the system that has this h to this input u. And that's the input u up there, okay? So what I do is I take the first value of u, I multiply that times the entire h, and I put it at that point in time. I go to the next value, next input value, I multiply that times the entire h, and I put it at this point in time. So, you see what I'm doing? If h is the response of my system to a single input at one point in time, and if my input is a combination of these, all I have to do is scale and shift that h correspondingly at each point in time, and then add them up. That's the total response. That's convolution right there. That's it. You can do this in high school. You notice I didn't talk about triple integrals. I didn't talk about any weird calculus abstract functions. All you need to know to do convolution is you need to know how to multiply something, you need to know how to add, and you need to know how to align something at a different point in time with a tabular form or something. That's it. No calculus needed, no differential equations needed, none of that. That's convolution. It's that simple, okay? So, again, this is the, I like the last bullet. What are memories of convolution? How many of you do recall doing convolution at any point? Raise your hands. Well, most of you try to forget it. Try to forget is that. But this is the continuous time, and so I'll show you what the breakthrough was. Now, here's the step response. You can do a step response, and you get what's called S, the step response to the system. Now, sometimes, in some systems, you find that they apply a step. This is going to be important for unsteady aerodynamics, all right? This is why I wish these things would have been covered when I was doing undergrad, because things are thrown at you. Here's Wagner function, here's this, and you're like, okay, wait, I don't even know what a step response really means. How am I supposed to understand what an unsteady aerodynamic function means based on a step response, right? So, sometimes it's easier to apply a step input to a system than an impulse, all right? If you have an airplane, it's sometimes easier to just take it from 0 alpha to 2 degrees and hold it. That's easier than applying this infinitesimal impulse input. So there's mathematical and physical reasons why you might prefer to do one over the other. Now, this is very important. The impulse response and the step response are related. They're relatives. One is the derivative of the other, okay? So, if I have the step response of the system, all I need to do is take the derivative of that step response and I get my impulse response, or the h, okay? But I can also perform convolution with a step response, so I don't have to get h. I can use just s. And the convolution integral changes a little bit from the original. Why? Because now, instead of h, you have s, Instead of u, you have the derivative of the input plus that term. So if you have the step response or the impulse response, you can perform convolution with either one, and they're both related. If one exists, the other has to exist. Okay? So, unstable dynamics and elasticity kind of started, let's say, in the 1930s. And back then, there were no computers, right? So a lot of things were based on frequency domain. You take a e to j omega t, you plug into your equations, you get your solutions, very elegant. But everything was based in frequency domain, and things tend to be in that nature. Then in the 1960s, came along digital signal processing. In the 60s, we started having computers. Things started to change. And so one important change that sometimes doesn't get reflected in the courses that we see is the huge impact of digital signal processing. It really is a science in and of itself. It's not just the sampling or continuous time signal, okay? And that's very important for you. I strongly recommend, how many of you have taken a class in DSP? Raise your hands. Okay. Strongly recommend that you either take a class in DSP or buy a textbook, or there's a lot of excellent free textbooks online. They're outstanding, very easy to follow. What you'll find in page 2 of chapter 1 of practically every DSP book is that it says, remember all that Dirac delta function stuff about going to infinity, epsilon going to 0? Forget about it. It doesn't apply anymore when you're doing digital signal processing, okay? That's an important concept. We tend to get stuck in a continuous world thinking when we're doing CFD and we're doing other things that are discrete. These are digital concepts. You need to bring the digital domain, digital tools into that environment, okay? So this is just quickly, this is how a digital signal is quantified. It's an integer, whereas a continuous signal is parentheses, discrete signal is brackets, all right? And it's only defined at sample points. So for example, here's a signal, and that's x0, x1, x2, and it indicates the location. You can have negative, mathematically speaking, you can have negative time. Physically, that's obviously not realizable, but there's reasons for doing that. But this is how you define a digital signal. And this is what the sequences are called in DSP. The unit sample sequence is, in fact, the unit impulse function. It's analogous, and no pun intended, it's analogous to the Dirac delta function. But here's the difference. It's 0 everywhere, but it's 1 at one point in time. And notice that it's not suffering from those issues or abstractions of the Dirac delta function. You don't have to worry about that. How would you apply that to your computer code? How would you apply a Dirac delta function to your computer code? Do you take it at this point and this point, or do you take it at this point and that point? Do you take it wide and low, or do you take it narrow and high? And there's an infinite number of combinations in there. Well, you don't. Dirac delta function is great for ordinary differential equations or partial differential equations, because those are called generalized functions and they're distributions. And you can use it to solve those and get, anybody remember Green's function? Green's function ring a bell? Well, just so you know, Green's function is the exact same thing as the impulse response function. Green's function is the H that I've been showing you. But we love to use different names to confuse people and to keep people wondering, right? It's just different names for the same concept, okay? And here's the unit step. The unit step is just a step, a series of constant inputs. And one is the derivative of the other. and this is how you would put it. So this is a value at time 0, that's at time 1, at time 2, and so on. So if it's plus 1, it's at -1, plus 2, it's at -2. That's just the nomenclature, all right? You can learn more about that. I'm not going to spend a lot of time on that. I just want to give you a flavor for what DSP covers. And notice, remember, I said the impulse response is the derivative of the step response. The same thing here. The unit sample sequence is the finite difference of the unit step response. Finite difference, because now we're talking discrete derivatives, which is the finite difference, right? So this is extremely important. Any sequence can be represented as a sum of scaled and shifted unit sample responses. So here's an input, and believe me, any input you apply to the system it actually is discrete because you've discretized it. It has so many, at a time step, it has a specific value. So even though visually it looks continuous, the reality is that it's very small samples, very small specific values. So that's what that input might look like. And here's how you would write it down. So it's twice delta at n equal -3, -1. So you're scaling, and you can shift it. So what will be the response of a system to this input? If you can take any input and break it down into this format, notice the beauty of it. So all I need to do is compute this delta once. I apply the delta to the system, I get that h. This is the h I'm talking about, right? Once I have that h, I just scale it by 3 and or shift it. Now, here's the bonus question. How many of these inputs do I have to compute for a given system? If this is a linear time invariant system, the beauty and the power, that's right. The beauty and the power of time invariance is that if I apply this input at time 0, what if I apply that single input at time 2? The response is the same because it's time invariant. So a time invariant system has one and only one impulse response, and that's the mathematical power of it. A time varying system, on the other hand, will give me different impulse responses at different points in time, so it's more complicated. You can still do convolution, but it just becomes more complicated. Okay? So let me break it down again from a discrete digital point of view what convolution involves. I have a discrete time, linear time invariant system. I apply the unit sample input, which is a value of 1 at time 0. Notice the summation of this function is equal to 1. What does that look like? Remember the integral of the Dirac delta function? What was the integral of the Dirac delta function? It was 1. Okay? So it preserves that quality. Then I get the h, which is unit sample response. So then I can perform this discrete time convolution. So again, the fact that it's linear, I need to compute the delta only once because if I have twice the input, I just have to do twice the output. The linearity gives me that benefit. The time invariance tells me that this, if I apply the input at a different point in time, right, it's just shifting it. The output's the same. It just gets shifted accordingly. That's why it's called shift invariant. Okay? So the response to this input, if this is the input that I have, the response to that input is just twice h at that point in time minus 1 h, because h is the response to a single one. But that h can be scaled, and it can be shifted. It can be scaled because it's a linear system. It can be shifted because it's a time invariant system. Okay? That's it. You're now experts in convolution. When you take a class in DSP or a book, you learn to do convolution by hand. If you have two signals, discrete signals, you go boom, 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 boom. You learn to do convolution by hand because it's very simple. All right? So if nothing else today, I want you to let go of the myth that convolution is difficult and realize that convolution is actually, you're doing it every day. Every time you use a code or something, convolution is working in the background. But it's also a way to predict something. It can be used for prediction. That's the whole point. That was never made clear to me. Undergraduate, I learned kind of to do convolution, but I didn't know what was the point. Why are we learning convolution? What is the whole point of convolution? I never understood that. Nobody ever told me. It's predictive. So here, let me show you an example with discrete system. If that's, this is the h, right? And that's the input I'm applying. I take twice, and let me show you. So I have that h on the right-hand side. I compute that once. So then, if this is the arbitrary input, I take twice that h, and I put it here. Then I take once that same h, and I put it here. I take 0, that h, I put it there. Then 1, that h, put it here. Add up the columns, I get the response. That's y. That's convolution, folks. Period. This is the way the convolution makes physical sense to me. Because what it's saying is that if I ping the system with a 2, I will get this response, but I may not see it. If I ping with a 1 later in time, I will get that response here. And that the final response is the summation of all of them. This goes back to the memory discussion. This is the memory of my system. And in some cases, if h was very long, you could see how an input at time 0 will have an impact many seconds later on. So convolution this way is extremely elegant, is very clear, is physically intuitive. But this is not the way that's taught. Okay? So, now, what you see here, you kind of, and when I teach this, I make students do this by hand. You can see here, you have to do each one of these, and then you add them up. So you may not know what y at time 2 is until you add everything up. But what if you want to know what it is at time 2 without having to do that? That's where this second method comes in. This second method says take one, flip it around. Won't go into details. I'll let you look this on your own. Just take it from me that what flipping around does is it gives you the answer at time 2 right away without having to do all of those and add everything up. This is just a mathematical contrivance that makes it a little more efficient to get answers for convolution. But this is not, in my opinion, the best way to understand convolution. This is actually the most confusing way to understand convolution. Okay? But unfortunately, this is what you'll see in most books. Any questions? So I won't go into this, but it's an example. And you can do this by hand. Exactly, do it by hand. You can go back and do it in your office later today, and then do it in MATLAB using that. The answer will be exactly the same. Exactly the same. Not approximately, exactly the same. So what would you do here? You take 1. What you're doing is make believe that those others don't exist. I just have 1. What is the response to 1? It's that. Now, make believe that this 2 is the only one. What is the response to a 2? Well, it's this times 2. It's all it is. It's scaling and shifting and adding. Discrete time difference, I won't spend a lot of time on that. There's order of convolution, does not matter. So again, I won't spend a lot of time on these things, but they're there for you. So, now let's go back to those quotes we saw in the beginning. By the way, autonomous. Somebody tell me what autonomous means. Well, I take a sip of coffee. It's just a ploy for me to get coffee. I throw questions out there. Autonomous. See, in math, science, and engineering, we love to come up with different names. In mathematics, we have autonomous, non-autonomous. In engineering, we have time invariant and time varying, but they're the same thing. Autonomous actually means time invariant. Non-autonomous is time varying. Why the different names? I have no clue. That is harder than anything I could ever imagine, okay? Figuring that out is really difficult. Math is easy. Figuring the reasons why people name certain things, I don't know. There's actually methods that in finite difference that you learn about, that somebody got their name associated with it. It's a method that is always unstable, never works, yet somebody got their name on it. How that happens, I don't know, but somebody became famous on a method that doesn't work at all. So now you see that this should be a lot clearer to you. Autonomous nonlinear system precludes time-dependent forcing functions. That's not right. The time invariance or the time varying of the system is the system itself. It's not the inputs. The inputs don't define the system, okay? So that's not quite right. That's a little misleading. Now, the last one, whereas the unit step function is well defined, the unit impulse function, mathematically speaking, is not. What's wrong with that sentence? I kind of said it before. If the step response exists, all you have to do is take the derivative of that. Therefore, the impulse response exists, okay? So that's not quite right either. All right, now, so you're saying, when we get to elasticity and unsteady arrow, this is the part that connects the unsteady arrow. If I don't walk you through those concepts, unsteady dynamics makes no sense. And if unsteady aero makes no sense, aeroelasticity will be very vague to you, okay? So those, in my opinion, have to be a solid foundation to get that. So we've learned that with convolution, if I have a system here, I apply a pulse, I get the impulse response. If I want the response of that system, if I want the steady response of that system, I just convolute it with a step, and I get what's called my steady or initial response. If I convolute it with simple harmonic motion, different frequencies, I can get the frequency response. If I convolute it with random, I can get random response. So once I have the H, once I have that impulse response, I can predict the response of this system to any input whatsoever. Okay? That's important. That's valuable. I like to have a tool where I have one function, and that function allows me to predict the response to anything. That's extremely efficient. Okay, so I mentioned this already before. You can still do convolution with time varying, but the problem is you have a family of impulse response functions, because at every point in time you might have a different H. For a time varying system, H is the same whether you're at 0 or at 2 seconds or 20 seconds. H doesn't change. I won't spend a lot of time on these. Just understand that one of the things you also see in convolution in your classes, engineering math 101 or whatever, professor says, well, here's convolution, this is the convolution integral. It's really complicated. It's convoluted. It's because it's convolution. So what we do is we take the frequency domain equivalent, because convolution in time domain is the same thing as multiplication of the frequency domain. All right? But now you know that convolution is not that complicated either. Okay? I won't spend a lot of time on these right now. Any questions? Okay. Again, I have a lot of charts, so I'm going to try and focus on the main concepts. Laplace transform becomes important for unsteady aero, for aeroelasticity. We'll cover that a little later on. So I won't spend a lot of time on this. But you can use Laplace for all kinds of things, of course. You've seen it. Now, this is important because this shows up in unsteady dynamics, this shows up in elasticity, this shows up in aeroelasticity. It's a root locus plot. How many of you remember root locus plot? Raise your hands. Okay. It's the eigenvalues of your system. And the eigenvalues of your system tell you the stability of your system. These are your roots. And you need to be able to plot them, real and imaginary. You'll see later, I can take an aeroelastic system, extract its eigenvalues, and plot them on a root locus plot, and I can show you, all right, everybody, this is a test. Are these roots stable or unstable right here? Very good. Okay, you pass. I'll tell the professors to pass you guys. Right? That's right. Left half plane, stable. Right half plane, unstable. Okay? So as soon as a root crosses the imaginary axis, you've gone unstable. And what you'll see for elasticity and flutter is we take our elastic systems, we put them into this form, and we track as dynamic pressure or velocity changes, and you watch when a root crosses into the right half plane. As soon as it crosses the imaginary axis, that's flutter. That's a flutter point. Okay? So you might be thinking, boy, he's talking a lot of math. Why don't you talk about elasticity? All of this is actually part of it. These are the tools that you need to really understand unsteady aero, really understand elasticity, and really understand aeroservo elasticity. Okay? See, as more roots, you have poles and zeros. And again, these notes might be helpful for you later on, but I'm not going to spend a lot of time on that right now. Now, this is important. Why is it that to extract the impulse response, why do we have a Dirac delta function? Or to extract the discrete equivalent, why do we use a unit pulse input like that? Why? Why don't I just use a sine function at 1 hertz, a sine function at 2 hertz, a sine function at 5 hertz? Because those are totally inefficient. If I want a response at each frequency, I'd have to apply a sine function at each one of those frequencies. So if I want 50 frequencies, that's 50 inputs. That's absurd, right? Because if you look at the Fourier transform of the Dirac delta function or the Fourier transform of the unit sample input, guess what? It covers all the frequencies. So physically what it's saying is, if I come here and I do this, I'm just exciting a broad band of frequencies, and that's what I want. When I'm doing system identification, I want to excite all the frequencies of my system in as efficient a manner as possible. If I do 1 hertz, 2 hertz, 3 hertz, up to 100 hertz, that's wasteful, that's silly. When I can just do that, and guess what? I get a whole range of frequencies. That's why the Dirac is important. That's why the unit sample input is important. Because when you apply it to a system, you ping a system with that input, you excite a broad band of frequencies, and that's what you want. You want to characterize the system completely. You don't want to ignore frequencies. You want to make sure you capture as many frequencies as possible. Now, theoretically, a wide spectrum doesn't really exist because that would require infinite energy. So you have color spectrums. They're banded. There's bands where there's limitations, okay? But this is the terminology that you want to keep in mind. And this is how, things can change. Things change from time to frequency, okay? Won't spend a lot of time on this. This just shows you that if you have convolution in the time, is multiplication in the frequency. And one or the other, vice versa. So, how can you use these transforms? And this is done a lot in unsteady aerodynamics. You have it in time. You can apply the input in time. If you have the h up above, y equals h star, that star, by the way, is convolution, okay? So I can compute y by using convolution of h with the input. That'll give me y. Another way of computing the response is I take the Fourier transform of the input, I take the Fourier transform of h, and because I don't do convolution and frequency, I do multiplication. I compute y as the product of h and w. Now, this is a complex mathematics here. So you got complex real and imaginary numbers. Then you take the inverse of Fourier transform and you get y. So I'm just showing you there's fluidity, and there's no pun intended, but there's fluidity with the methods you can use. You're not bound to one or the other. These are all tools for you to use any way you want, okay? Whatever's convenient. All right. I'm not going to talk a lot about this, but let's go ahead and take a 5-minute break right about now. And we'll come back for the next section. Any questions? All right. Very good. That are important for aeroelasticity. So you may remember in '65, Cooley and Tukey published the landmark paper, the fast Fourier transform. We know about the Fourier transform, but the fast Fourier transform really enabled huge revolution. Dramatic efficiency, by taking advantage of the mathematics of symmetry and periodicity, you develop the FFT. Without the FFT, we wouldn't be able to do a lot of what we do today. In wind tunnels experiments, we have frequency analyzers. You plug them in, and you get the frequency content on the fly. That's thanks to the FFT. If we're still doing traditional Fourier transform, that would never happen. Okay, that would just not be possible. So the huge benefits, for example, as can be seen there, is that if you use a traditional Fourier transform, it's on the order of n squared. So 2 to the 20 would be 1 million. For the FFT, it's actually n log 2n. So you're talking about a difference of 1 million versus 10,000 number of operations. So it's one of the most important algorithms that are created. If you're not familiar with it, make sure you use it quite a bit. I encourage time and frequency domain. You need to be very comfortable with that. How many of you use FFT routinely? Raise your hands. Okay. Encourage you to play around with it. There's a lot of important information there, okay? The other part related to discrete is called the Z transform. Won't spend a lot of time. But the important part is that it's analogous to the S-plane. The S-plane is the root locus that you're familiar with. But the S-plane is continuous, right? So this is continuous, which means if this is damping and this is frequencies, frequencies go out to infinity because it's continuous. As soon as you discretize a system, you sample it, you create what's called an Nyquist frequency, and that's the upper limit. So let's say I sample and the Nyquist frequency is here. What the Z-plane does is basically take these two ends and put them around in a circle, right? So you've taken them and folded them, and so now this is the Nyquist frequency. The Z-plane, if you look at the discrete time functions, if the poles are inside the unit circle, that's a stable system. If the poles are outside the circle, it's an unstable system. Why? Because The left is what's stable. So the left is actually what's inside the unit circle. Anything outside of that is unstable, all right? So again, these are tools that you might come across, certainly in aeroelasticity. Not going to spend much time here. Again, I'll give you all these notes. You can look at issues like aliasing and sampling frequencies and all these things that are extremely important. Make sure you understand. Influence functions and Green's functions. This is important in aeroelasticity, structural dynamics. For example, if I have this beam, I have these three forces. We know that F equals kx, right? Force is the stiffness times the deflection. What if you don't know what the stiffness matrix is? So what you do is you excite one force at a time. So if I apply a unit load at this position, I measure the three deflections, that gives me one column. If I apply a unit load at the F2 position and I measure three deflections, that gives me the second column. And likewise for the third. So this is a way that in elasticity, and aircraft manufacturers actually use this method to measure the stiffness of a vehicle. It's called structural influence coefficients. Structural influence coefficients is a way to generate the stiffness matrix for a system. Guess what? You have aerodynamic influence coefficients. What is that? If you have boxes, if you have a linear panel method, and you have a box, you have 100 aerodynamic boxes, aerodynamic influence coefficients say, if I perturb the aero in this box, what is the response of that perturbation aerodynamically on all the others? So, and I do that 100 times, and that gives me the aerodynamic influence coefficient matrices. Those are two standard models that are used quite a bit in aeroelasticity, in unsteady aero, in industry, and still in some research government areas, okay? But understand where it comes from. It comes from these very simple concepts of defining that. And just like with the impulse response, once you have K defines the stiffness of this beam. You don't need to recompute that every time. Once you have it, you have it. And for any deflection, you can compute the forces, okay? It's the same exact concept, okay? Just a different manifestation of the same idea. So I won't spend time on this. So this is what I'm talking about. Aerodynamic influence coefficients. These are AICs. These are important in unsteady dynamics and aeroelasticity. Structural influence coefficients are also important to determining how the structure deforms and bends, because elasticity, as you'll see later, is the interaction of unsteady dynamics and structural dynamics. But these are all based on the same concept. All right, this one is very important. How many of you are familiar with state-space equations? Raise your hands. Okay. Here again is a topic that's not usually covered, but it's extremely important for us in aeroelasticity and aeroservoelasticity. So I'm going to talk to you about what it is. Why do we do state-space equations? What is the whole point of state-space equation? Well, let's say you're given an nth order differential equation. Say you have a 10th order differential equation. How many of you are eager to solve that right now? You want to go back to your office and solve the 10th order differential equation, right? I mean, that's, well, you still have the weekend. So you can certainly work on it Saturday and Sunday, right? I mean, nothing else to do, right? But the whole point of state space is as follows. If you have a single 10th order differential equation, you can convert that into 10 coupled first order differential equations. So would you rather solve one 10th order or 10 first order? The 10 first order always wins because they're coupled, and because what's the solution to a first order differential equation? Come on. This is kind of a qualifier question. It's exponential. The solution to a first order differential equation is always exponential. It doesn't matter if it's matrix, it's still exponential. If you have 5 orders or 20 orders, it's still what's called a matrix exponential. So it's significantly more efficient. And so this is how you do it. What you're doing is you assign a state to every derivative. So these are called state variables, and a derivative is given a state variable, okay? So then you line them up as follows. You say y1 prime is y2. Let me so you don't get confused, let me kind of show you that. If y1 is y, y1 prime is y prime, which y prime, as you can see, is y2. All right? So you line up the relationships. This is what couples the equations. This is what couples the equations. You have them coupled, and then the last one actually has your actual function expressed as the state variables. This is what's known as state space form. State space, is it linear or nonlinear? Somebody? Anybody know? Either or. There's a misconception that state space is linear. That's not true. You can put a nonlinear equation into state space form, and in fact, you want to do that, and you need to do that. If you look at the theories of nonlinear dynamics, when you look at the theorems and the analysis, all nonlinear equations are put into state space form because it simplifies the analyses, it simplifies the theories, it simplifies things like equilibrium points, and all those things are much easier to compute if you have it in state space form. All right? So let me show you how this works. An example, mass spring system, which I'm sure you guys have seen once or twice throughout your undergraduate careers. This one along with the pendulum, right? It's like everywhere you go, it's a mass spring system or a pendulum. So what you do is you say y1 prime is y2, and y2 prime, which is the y double prime, is equal to everything else set to the right-hand side, but now it's a function of the states. Notice, a second-order differential equation will give you a state space equation with 2 equations. 10th-order differential equation will give you a state space equation with 10 equations. That's how it works. All right? If you don't get that, you did something wrong, and there's a mistake. Now, because this happens to be a linear equation, and because these coefficients are constants, we can put it into what's called linear state space form. And that is as shown here. And so you have y prime equals ay. And this is how you create, for example, a structural dynamic system. This is how I create it. It's very simple. Because what's k over m? Omega squared. So if you have 10 modes, you have a matrix here with 10 diagonals, a diagonal matrix that has all the 10 frequencies of the modal system. Okay? And that's all there is to it. But this can be made into linear because, again, the coefficients are constant. Now, if you have inputs to the system, you can add that BU component. B is called the input matrix. And then you can also have what's called the output equation. So this is the integral part. These are the inputs to the system, and these are the outputs. And you can set it up any way you want. This is really user-defined. This is the part that gets integrated. This is the part where you pick and choose which of the states that you want to look at, right? If you have a 10th order, 10 states here, maybe you don't want to look at all 10 states. Maybe you only care about the 2nd state and the 8th state, in which case then your C matrix correspondingly is a 1 for the 2nd and a 1 for the 8th, and 0 everywhere else. So this part, you pick and choose the states that you want to analyze, the states that you want to look at. But this part is hardwired. This is the pure integration part of the equation. This is where actually the ODE gets integrated. So we take elastic systems and we put them into state space form. Okay? And the beauty of that is that the A matrix is known as the system matrix. All you have to do is look at the eigenvalues of the A matrix. That gives you your root locus, and that gives you the stability of your elastic system. Yeah.
And here you sort of made the assumption that you can write the ordinary differential equations as explicit equations. Does any of this change when you cannot do that and you only have implicit differential equations?
There's a couple ways to tackle that. The other way that I do it, that we can create state space equations, is with system identification. If I apply inputs and I apply outputs, there's mathematical procedures that will generate a state space equation for me, whatever's embedded in that system. So I can treat that system as a black box, which sounds is more along the lines of what you're thinking about. So whatever's in there, if I can't tease it out, which I think is what you're saying.
Yeah, well, can you go back?
Yeah.
here. Let's say that you're not quite able to do this. Let's say that that last equation has one of the derivatives in it on the right-hand side, and there's no way of getting it out of this.
Okay.
Then you can write an equation with y1 prime minus y2 equals 0, basically makes the whole equation
Right.
0.
Right.
So, one or more of the equations are implicit. Does any of this change? Interesting if that's the case. If not clear all the derivatives.
Yeah, that would be an issue. I haven't come across that myself. I have not come across that. In all the stuff we've done with elasticity, unsteady aero, reduced order models, I have not come across that situation.
Okay.
Mathematically, conceivably, it's possible, and it would change. But experience-wise, I have not seen that. So, okay. Now, the other part is system identification. The beauty of system ID is that it says, maybe I don't know what this black box is, but if I apply certain inputs U and I measure the outputs Y, I can actually create the ABCD matrices. That's what system identification does. And it turns out that the impulse response, H, that we've talked about, is actually mathematically related to the ABCD matrices as follows. So it works several ways. If I can compute the impulse response of a system, H, I can back out the ABCD matrices. And that's, in fact, what, in many ways, I do with my reduced order modeling method, and that's what's done a lot of times in other aeroelasticity and aeroelasticity methods. Okay? Any questions? The reason we use state space, again, is because you can put everything into first order. And the solution of first order ODE is always exponential. So if it's 10th order matrix or if 20th order, it doesn't matter. It's still an exponential. And that's the beauty, and that's the appeal of putting everything you can in state space form, because it's easy to work with, okay? It's very convenient. And if this is the equation, if you solve it, look at the solution of this state space equation. If you solve it, expand it, what is this here? Somebody tell me what this is. And you get an A. I swear you'll get an A. I'll give you an A right away if you tell me what this is. I want to hear it. Thank you. You all get A's, all right? So you see, whether you realize it or not, when you're doing state space equations, convolution is embedded in there. Convolution is in there. It's always in the background. You're just not aware of it explicitly. Okay. And likewise, there's discrete time equivalence. So here, for example, you can see this system. Real quick, tell me about this system. Is this linear or a nonlinear system? I mean, we don't have to prove it right now, but what do you think? And why? Is it linear or nonlinear? Look at the y squared at the end. It's nonlinear because it's a y squared. Is it time invariant or time varying? What's the point that identifies that? What has to show up explicitly in the equations? Time. Do you see time anywhere in there? T? Do you see a T? No, so it's time invariant. So this is a nonlinear time invariant equation.
Yeah, but couldn't UA be time?
But it doesn't matter, because the classification is for the system, not the input. That's the important point, and that's what sometimes gets garbled up. When you classify a system, for example, when I classify a mass spring system, I don't classify what input I apply to it as part of the system. It's the system itself. Does that make sense? Yep. That's extremely important. So please, I'm glad you brought that up, because that's a common issue that shows up. What about the input? Forget the input. The input doesn't matter. Okay? Excellent. Very good. So here we can convert this into state space form. This is how you would do it. If you linearize it, you can put it into that form. And again, I won't spend a lot of time on this. Okay? And here I'm showing you in MATLAB how you would take this, convert it, discretize it, look at the z-plane, root locus. You see the roots? The poles are inside the unit circle, so this is a stable system. This system is stable. let me talk a little bit about system ID. How many of you have heard of system ID before? Raise your hands. Okay. A number of years ago, I started working, after I graduated at a company, I went to a conference, and there was aerodynamics and structures, and one of the sessions was system identification. And I'm thinking, what the heck is that? What does that mean? I mean, are you walking around saying, okay, that's a refrigerator, that's a dishwasher. What does system identification mean? And this is what it means. Essentially, you have a system, some sort of black box, for which you don't have any mathematical description. You don't have the equations for that. And that happens quite often, believe it or not. But maybe I can apply inputs and I can measure some outputs. And so applying certain inputs and outputs and measuring them, I can actually use mathematics to give me an approximation, a mathematical approximation of that system. But that's why it's important for you to know. Am I dealing with a time invariant or time varying system? Am I dealing with a linear or nonlinear system? If you don't know those things, you're not going to be able to apply this properly, and you're not going to be able to generate a valid or accurate mathematical representation. Okay? It's parametric, non-parametric. Again, I won't spend a lot of time on these things. You've heard of black box, but there's other boxes. There's white box, light gray box, dark gray, and it depends on how much information you have about the model. When you don't have any information, zero, that's a black box. The white box is when you kind of know the equation. You know the type of the equation, you know some of the parameters, but you're trying to home in on, is it this mass or this stiffness? You know, how much is that? So just give you a sense of the, of the terminology, okay? There's time domain, frequency domain. We've talked about these things. Single input, single output. Let me move on. State space is important. So you can take inputs and outputs and put everything into state space form, okay? Orthogonality. We talk about orthogonality, basis functions. Extremely important when you talk about decomposing functions. That's something else we do in Unsteady Aero, is we decompose functions into other methods. How many of you remember hearing about orthogonality? Raise your hands. It's one of those things you invoke, right? Doing your homework or exams, imposing orthogonality, you use it like this, this free thing without really being 100% sure what it means. But it's an important concept. All it means is that you get rid of any redundancy. Things are about as different as they can be from each other mathematically, okay? Again, these are all concepts that are important. I'm not going to spend a lot of time on these. Nonlinear systems is the next extremely important topic. I will spend some time on this because this is essential. How many of you have taken a formal class in nonlinear dynamics or nonlinear systems? Raise your hands. Okay. This is very, very important. So, 1600s, Newton's physics, calculus, there was a time we thought everything was deterministic. Everything was a clockwork. If you knew this, you knew that, you could predict everything. Along came Lorentz. We came across turbulence and chaos. Fractals, we realized it's not so simple. It's not so deterministic. The real world is nonlinear. I hate to break the news to you. The real world is nonlinear, often quite nonlinear. Turns out, you know how you learn through most of the undergraduate school, you learn a lot about linear methods. It's one of the main things that's taught. Well, when you take a class in nonlinear dynamics, there's actually a theorem in nonlinear dynamics that says that you can take a nonlinear equation, nonlinear function, and it's valid for you to do a local linearization and create a linear model. So nonlinear systems theory gives us permission, gives us mathematical permission to create all the linear systems that we're so happy about, okay? But we're not told about that. We're not told, here's some linear systems, and by the way, nonlinear systems theory allows us because it's too much at that point in time. But understand, linearity is a very tiny subset of a much more real nonlinear world. Understand that. That's very important to understand. Some folks tend to, and I see at conferences all the time, they have a nonlinear problem, they come up with a linearization, and then they use the linearization everywhere. They use it everywhere, at all conditions, all solutions, and things don't match up quite well all the time. I'm not sure why. Well, it's pretty obvious why. You're abusing the validity of the linearity. Okay, that's something you got to be careful not to do. Okay. Differences between linear system and nonlinear. Linear system moves towards equilibrium point or blows up. Those are the only two options for a linear system. A nonlinear system has greater complexity. A nonlinear system has multiple equilibrium points. We're going to talk about what those are. Multiple equilibrium points. So it could be bouncing from one equilibrium point to the other. It's very complex, which is what makes it that much more interesting. Exact solutions are rarely available. So here's what a linear system could do. A linear system, if it's stable, I can start from different initial conditions, and it's always going to go to the same point, always. It doesn't matter where you start. If it's unstable, it goes to infinity as time goes to infinity. Nonlinear system, on the other hand, has multiple equilibrium points. So depending on the initial conditions where I start, it could go to that one, or it could go to this one. I mean, this one could be really, really close. This is called sensitivity to initial conditions. Depending on where I start, it could go to that one, or it could go to that one, and then come back to this one. This is what creates the complexity in the nonlinear systems. Now, nonlinear systems also have a finite escape time. They can go to infinity in finite time, which a linear system can never do. Okay? This is important dynamics because in elasticity and steady error, we deal with nonlinearities all the time, and it's becoming a bigger and bigger problem. We're dealing with vehicles that deform significantly. That's nonlinear structural dynamics. We're dealing with vehicles that fly transonic with pretty thick airfoils that create strong shock boundary layer interactions. That's nonlinear unstable dynamics. So if we don't understand the nature of nonlinearity, the mathematical principles, we're not going to be able to understand the physics, and we're not going to be able to model them appropriately, okay? So that's why it's important for you to invest time in some of these thoughts. Okay. So again, I said state space is powerful, convenient for nonlinear systems. You can put it in this form, so it doesn't have to be a matrix form. So let's look at a pendulum, right? Simple pendulum, that's the equation over there. This is how you put it into state space form. So notice, this is state space form. It's not in matrix or linear state space form. Why? Because I can't put that sine of x1 into a matrix. x1 and x2 can't be row vectors because I can't have sine of x1, sine of x2. That makes no sense mathematically, right? Equilibrium points. How many of you have heard of equilibrium points before? They're called fixed points, critical points. It's the same, again, 3 terms for the same concept. Equilibrium point, fixed point, critical point. It's all the same thing, all right? So knowing the number and type of equilibrium points provides insight to the complex dynamics, all right? So equilibrium point is where the solution space of the system, where the system is at rest. So let me go back. System is at rest. When is the system at rest here? When the derivatives are 0. So if I set these two to 0 and solve for x1 and x2, that's going to give me the equilibrium points for that nonlinear system. Okay, it's that straightforward. So here, I set that to 0. The equilibrium points are sine of x1 are 0, or x1 is a multiple of pi. And so you see, you can view it in time. Those are the equilibrium points. And that's the phase plane where you have x versus x dot. Again, won't spend too much time. But these are different equilibrium points a nonlinear system can exhibit. It can have a stable node or unstable node. It can have a spiral, saddle point, center, just terminology, all right? I'm not going to spend a lot of time on that, but the important thing I want you to walk away with today, nonlinear system has multiple equilibrium points. That's what makes it so complex and predicting its response so difficult. A linear system, by definition, has one and only one equilibrium point, okay? So here's kind of how the pendulum actually has 2 equilibrium points. You see that? What are the 2 equilibrium points of the pendulum, physically speaking? One is right here at 0, right? If I let it go, it comes back to the 0 stable point. But there's another equilibrium point to the pendulum. What's the other equilibrium point? This is worth 40 points now. Are you keeping track of your points? Because I don't give these out for free. You know, what's the other equilibrium point? Very good. This is the other equilibrium point right here at 180, at pi. But it's an unstable equilibrium point. But the system, mathematically speaking, is at rest there as well. So you have a stable equilibrium point because it wants to come back here, and you have an unstable equilibrium point. So there's two equilibrium points. And when you plot it, this is theta versus theta dot. You can see it here. Here's the stable one at 0. So if I release the pendulum from here, it wants to come back to this point. Here's the unstable one. If I release it from here, it goes away. It goes either to this or to that, which is another multiple of 0. Okay. So that's that's what I want you to understand. You can linearize using something called Jacobian. We won't talk a lot about that, but you can take a nonlinear system. So let's say a nonlinear system has 5 equilibrium points. You can linearize that nonlinear system at each one of those equilibrium points. So if a nonlinear system has 5 equilibrium points, in theory, you can have 5 local linearizations. But that's the only way you linearize. You can only linearize about an equilibrium point. So that's why, by definition, a linear system has one and only one equilibrium point, because that's where it was defined. Okay? It's important for you to understand the origin of these concepts, of these terms, and of these words. Okay? And it can be stable or unstable if you look at the eigenvalues. So again, I won't spend too much time on this. Just understand that if a nonlinear system has 5 equilibrium points, it can have 5 local linearizations about each one of those equilibrium points. That's what that means. Okay, there's a van der Pol. There's, yeah?
So you cannot linearize about some other place in space?
No, because you got to go to a place where the system isn't continuously changing. If it's continuously changing, you can't get a local value. You can't get a local function there. It has to be about an equilibrium point in order to get a valid linear model. I mean, you might be able to come up with an equation, but it's not going to mean much. Okay. Any other questions? All right. Again, there's a lot of stuff here. It's never the intent to go through all this. This is the logistic equation we talked about earlier. It's a very simple equation. You see the parameter r? If I set r equal to 2.2, I get that simple solution. 2.8, you get a little bit of dynamics. 3.5, you get this point. Now, each one of these, so you see it's one equilibrium point. There's one equilibrium point. Here, it's going between 2 or 3 equilibrium points. And there, it actually becomes chaotic. From this, you can create what's called a bifurcation map. And you've seen this before. This is a bifurcation map for a nonlinear system. What it says is, as r changes, at r 2.6, I have one equilibrium point. At r equals 3.2, I have 2 equilibrium points. And I go up to 3.9, I have chaotic response. But notice the chaos is contained. It's contained within a certain region. Okay? This is one simple example that is worth investigation if you ever get a chance. There's also another important nonlinear equation or system is called Duffing. This shows up in nonlinear structural dynamics, nonlinear structural stiffness and elasticity, so an important one for you all to be aware of. Again, don't want to spend too much time on these. Now, finally, unsteady aero. So, early developments were 2D flat plate and compressible flow linear equations. Why? Because we didn't have computers, we didn't have iPods, we didn't have iPads, we didn't have supercomputers. Okay? It was all pencil and paper, or quill, quill and ink. And there's functions such as Wagner's, Theodorson's, and we'll talk about what those are. But then all of a sudden, geometries got complex, and the flow became compressible. So we had to move beyond the classical unsteady aerodynamic theories. So you have things like doublet lattice is a method that's linear. It's basically a linear frequency response method. And it's still used quite a bit in industry. It's the industry standard. Doublet lattice or Z-aero, these are linear frequency domain unsteady aerodynamics. They don't capture the airfoil thickness. They capture only the plane form. They don't look at, there's no viscosity. It's irrotational, okay? So, but they work very well for a certain range of flight conditions. And industry has a lot of confidence in these methods because they've used them for so many years, okay? So let me talk a little bit about some of these. Again, I won't spend a lot of time on these, just talk about some of the major points. There's actual flows are three-dimensional, viscous, compressible, and nonlinear, but you can simplify these things significantly. Viscous or inviscid depends on, of course, the Reynolds number and Mach number. This is a terminology. You have anything less than 0.3 roughly is incompressible. Anything above 0.3 considered compressible flow. So the equations change accordingly. Again, this is more a couple different regimes. I'll talk about what these are. Subsonic, less than. Now, this is very important. How many of you have heard transonic before? Raise your hands. Okay. At what condition does the flow become transonic?
When the airfoil goes supersonic.
Very good, excellent. That was a trick question. That's a trick question. Why do I ask that? Because I hear folks, again, pretty knowledgeable people, talk about, well, we're flying at Mach 0.9, so the flow's transonic. You don't know. You don't know. You can't say Mach 0.9 is when transonic flow begins. It depends on the configuration. If you have a very thin airfoil, their airfoil may not encounter any supersonic flow locally until 9.8. If you have a thick airfoil, that airfoil will encounter some supersonic or mixed flow at 0.8. So you cannot ever say, and if any of you ever catch somebody saying that, correct them and tell them I sent you. Yeah.
And
Do you agree with that, what I'm saying?
I mean, and I've heard that on some, large aircraft with a lot of high lift devices.
Yes.
On takeoff,
Yes.
definitely the free stream value is subsonic,
Yes.
but you can get local supersonic flow because the suction peaks are so
That's exactly right.
high. You're still going at like Mach
Point.
1,
Yeah,
0.2.
that's right. So, don't ever listen to anybody who tells you that transonic flow is at Mach 0.9. Take them to task. Tell them, I thought it depended on the configuration. And it does. Depends on the configuration, okay? So be aware of that. It's one of my pet peeves because I see that all the time. People talking about it, and it really, really irritates me. So please don't ever do that in front of me.
And you see it very clearly also with very blunt bodies. Like
Oh.
I mean, we watched, on the TDT,
Yep.
the flow clearly exhibiting compressibility effects
Completely.
at very low Mach numbers.
That's right.
Because the body is so blunt.
That's right. So keep in mind, these conditions are based on the configuration, all right? So here's transonic flow. It's when you have mixed flow. As soon as you see something on the airfoil is supersonic, now you have mixed flow. And that's what makes it transonic, okay? Supersonic flow. So let me just give you a sense in aeroelasticity, there's codes that have been generated over the years, codes that deal with subsonic flow that are linear, codes that deal with supersonic flow that are linear, codes that deal with hypersonic flow, such like piston theory, for example, that can be linear or nonlinear. And then for the transonic regimes, we deal with CFD because there's nonlinearities there that you just cannot model with the linear equations. You have to take into effect airfoil shift, you have to take into effect viscosity, you have to take into effect all these parameters. So that's kind of the strip theory, something I used in industry when I first started many years ago. It worked very nicely. Works very nicely for certain configurations, for, again, subsonic and linear flow. Doublet lattice is one that you want to know about. Doublet lattice is one of the standard methods for computing unsteady aerodynamics. It's in the frequency domain, okay? So if you ever hear doublet lattice, you'll know, hey, that's for aeroelasticity. That's exactly right, okay? It's one of the standards. It's used in industry. Notice, airfoil shape doesn't matter. This is linear, inviscid flow, irrotational. You have these boxes and use these boxes to compute unsteady aerodynamics. But what is different is that doublet lattice allows for shape deformation, which is what we need in aeroelasticity. So if you have mode 1, mode 2, mode 3, you can account for that in doublet lattice and compute the unsteady dynamics, the effect of this mode on that mode, the effect of this mode on that mode. You can compute, what are those called? The influence functions. These are all influence functions. How does one mode affect the other aerodynamically, and so on. That's what doublet lattice does.
Well,
Yeah.
can you model camber with doublet lattice?
completely flat. It's completely flat. And so this is the equations. If you have the downwash, which is the actual motion, versus the pressures, you can compute what's called the kernel, and that gives you the answer. It's a very popular method. It shows up if you have Nastran. Nastran has an aeroelastic supplement. Doublet lattice is one of the primary codes that's in there for computing unstable dynamics for subsequent use in aeroelasticity. All right, so that's what you'll want to keep in mind. I give you some consideration. Now, remember this chart I showed to you before, talking about convolution. Turns out we can have something very fundamental here. It's the same image, but now we're talking about unstable dynamics. If I apply unit pulse and I get my impulse response in lift, for example, if I use convolution with a step, I get the Wagner and the Kuznets functions. Now, Wagner function is a linear 2D incompressible flow. What is the Wagner function? Wagner function is if you have an airfoil at 0 degrees angle of attack and you impulsively, boom, lift it up to 1 degree angle of attack. You do a step input. So the Wagner function is the step response to a change in angle of attack, to a change in a step, change in angle of attack. That's your Wagner function. Now, how do you use that? Well, you use convolution. If you have the step response of any system, you can use convolution. So now if I want that airfoil to go through some weird alpha maneuver, I use Wagner function, which is the step response, use convolution with whatever input you want me to predict. I use convolution of that and gives me the response of the system. Okay? That's why all that is important, because unsteady aero is based on all of those concepts. The Kuznets function is the same idea except for a gust. If you have an incoming gust, you have a 1 degree change in a gust, but it's the same step response. So those are just step responses. If you think of them that way, it simplifies the problem so much more. If I convolute it with simple harmonic motion, different frequencies, I get what's called the Theodorson function. That's a classic unstable dynamic theory for elasticity, but it's just the sinusoidal, it's the frequency response, if you will, for unsteady aero. Sears is the equivalent frequency domain for gust. So a lot of things you see in unsteady aero is there's some for the configuration, and then there's an analogous one for gust. Those two tend to go hand in hand, okay? Doublet lattice is frequency domain. It's basically, now Theodorson is linear 2D incompressible. Doublet lattice is 3D linear compressible. So doublet lattice, think of it as an extension of Theodorson to a more realistic scenario and environment. Yeah.
Well, a gust just works its way through the airfoil, and the Wagner function is for step angle of attack.
Right.
What if you have a pure heaving motion in which the combination of the Wagner and Kuznets functions, or how do you model pure heaving?
Yeah, you can include that because a heave is actually change in angle of attack. So you can combine that in ways with either one. So yeah. And then you can do random response as well. Okay, so unsteady aero is filled and loaded with all this stuff. Now Navier-Stokes equations is important because what happens when we're talking about different Mach numbers, if you talk subsonic and the dots are linear, I'm sorry, the dots are linear, and the line is the real, this is a flutter boundary. Let me walk you through this. Dynamic pressure versus Mach number. Anything below that line is stable. Anything above that line is unstable. And flutter, I'll show you a video later, is when a vehicle goes unstable. The structure can be destroyed, okay? It's pretty dramatic, and it's a huge safety issue that has to be addressed. Now, if you're in the subsonic regime, the dots are linear predictions. Those do pretty well. If you're supersonic, beyond what's called the transonic, linear methods can do pretty well as well. But if you're in the transonic regime, linear methods do not work at all. That's my walk-away message to you. If you're dealing with transonic methods, you cannot use linear methods. Transonic, do not use doublet lattice. If you know it's transonic, if you're guaranteed, if you looked at pressures and you know it's transonic, doublet lattice will not work. So then you have to use some sort of CFD, computational fluid dynamics, okay? Now, what I want to show you here is that all these theories have the same genealogy. Nobody made this stuff up. Nobody just one day said, let me invent doublet lattice. No, doublet lattice has a very important genealogy. Like everything, It comes from Navier-Stokes equations. You make certain assumptions and remove viscosity, you have Euler, you have full potential, transonic small disturbance, linearized, and more assumptions, here you have doublet lattice. Okay, so understand that all these theories, they're all related. They just have different levels of assumptions and things that are included or not included. These are the details of the equations. I'll let you look at that when you get these notes. I won't spend time. Additional terminology. From Navier-Stokes equations, you have direct numerical simulation, then you have large area simulation, Reynolds average, Navier-Stokes, and thin layer. The ones being used most nowadays are what's called RANS, Reynolds average, Navier-Stokes, and I'll talk about what these are. How many are familiar with this terminology? Raise your hands. So you've seen some of it. Okay. So DNS is the full and exact solution of the Navier-Stokes equations without any turbulence model approximations, all right? The requirements are huge. You could do 10 to the 18 flops, wide spectrum vortices, and that's why it's limited to simple geometries and low Reynolds number, because the grids, the solutions would take lifetimes to solve. But this is the exact solution. If you make some approximations, you simplify it, you focus only on the large, what's called large energy scales of the turbulence. You can make approximations to the Navier-Stokes equations and you end up with LES, which is large eddy simulation. There's actually quite a bit of LES being used nowadays. You see LES being done not routinely, I don't want to say routinely, but more frequently than it has been in the past, because compute power has enabled that, all right? So you'll see some of this show up. Now, the Reynolds average Navier-Stokes, what happens is you look at stationary turbulent effects or time average. So any sort of turbulence, you do a time average, again, mathematics. It shows up everywhere, man. It shows up everywhere. It shows up in everything. So you need to understand what's being done. But the time averaging creates more equations than unknowns, and so that's called the closure problem. And so you come up with turbulence models. You hear Spallard-Almaras turbulence model, K omega turbulence model. These turbulence models are mathematical equations that approximate some of those steady averaging results and fits all the equations. So now you have enough equations, enough unknowns to solve the problem. RANS, so now you guys can walk around saying, yeah, RANS, you sound really cool because now you know what the RANS means. It's Reynolds average, Navier-Stokes. It's one of the most common. If you use Fun3D code, which is very popular one here at Langley, unstructured code, that's a RANS code. Okay, so now you have the terminology to make some sense out of these concepts. And you can also use a thin layer for certain derivatives. So there's more and more approximations, okay? Other equations, again, won't spend a lot of time on these. These are Navier-Stokes. This is important because I want to show you how you can get different answers for different results. Now, this is called the flutter speed index versus Mach number. And so again, anything below here is stable. If you cross this line, the structure goes unstable and it flutters. It gets destroyed. And so different CFD results give you different answers. Now, what I want to show you, the dashed line is CAP-TSD. CAP-TSD is a code from the 80s, computational elasticity program, transonic small disturbance. It's a pretty nice code, has some limitations, but it works pretty well. And there's some experiment. Notice this is the experiment, okay, of the AGARD 445.6 wing tested in Langley's Transonic Dynamics Tunnel, which is where I work at the TDT, in the 1960s. Notice that the dashed line, which is linear, predicts this pretty well. Now, if you ever read anything in elasticity, you're going to hear a lot about the 445.6 wing. It's the most popular wing that's used in elastic analysis, validation, and so on. And you're going to come across papers that tell you, oh, my CFD code is great because it can predict this highly nonlinear transonic flutter dip here. That's wrong, okay? Wrong. First of all, this wing is a 4% thick airfoil. It's very, very thin. This wing does not become transonic till 9.8, okay? So you have a drop in the, this is called a drop in the flutter dynamic pressure, and people tend to call it the transonic flutter dip. But it's not transonic if the wing has not gone transonic yet. Compressibility alone, compressibility can cause this drop. So understand that. It's not just transonics that cause this drop. It's compressibility as well, okay? So be aware that there's a lot of work out there by folks, different organizations saying, my code, my super fancy CFD code is fantastic because it can predict this highly nonlinear transonic flutter dip. It's not, it's wrong. It's not highly nonlinear because my linear method predicts it very well. So keep that in mind, all right? Don't be fooled by these types of discussions. In aeroelasticity and unsteady aero, we sometimes have compensating effects. This is important for you to know. You have linear inviscid with flat plate, for example, a doublet lattice. If you add the thickness, accuracy is not usually improved. Believe it or not, sometimes you get a worse answer by going from like doublet lattice to Euler. People think, well, I'm going Euler. I'm doing CFD. I'm running a fancy code. I'm getting colorful fluid dynamics. I'm getting nice, colorful images. So therefore, the answer must be more accurate, right? Not true. Not true. Sometimes just adding thickness without adding viscosity is not going to help you. Actually, it makes the answer worse. When you have viscous effects, then it's improved. Okay? So keep this in mind. This is an important issue. For me personally, in aeroelasticity, unsteady aero, if I'm going to run something, I'll either do something linear or I'll do full Navier-Stokes. I'm not as crazy about doing Euler. I might do Euler to check out a few things, but you got to be aware that higher fidelity doesn't mean higher accuracy. Keep that in mind. Higher fidelity doesn't mean higher accuracy. Okay? Shock flows and stuff. All right, so now let me talk about aeroelasticity. I'll start off on aeroelasticity. How many of you have come across aeroelasticity before or raise your hands. Anybody? You have? I know you have. So it's, as you'll see, it's a discipline that involves multiple disciplines and multiple methods, which is why I spent initial time of this short course for you to understand the language, you understand the concepts, for you to understand the building blocks. If you don't understand those, none of this will ever make sense, all right? So I focus on that because it's important. When you perform elastic analysis, you look at all altitudes of interest, Mach numbers, and again, we'll talk more about this here in a minute. So this is what does an aeroelastic model mean? It's multiple things. It's a model of the structure. You need a model of the structure, which is a finite element model. How many of you have worked with or work with finite element models? Raise your hands. Okay. If somebody asks you that they want some aeroelastic analysis performed for a vehicle, your first question to them should be, do you have an FEM? Okay? Then I say, well, it's aeroelastic analysis, don't you have unsteady? You cannot do good quality aeroelastic analysis without a good quality finite element model. Because aeroelastic analysis depends completely on the structural response, on the structural mode shapes. Without the mode shapes, you're wasting your time, okay? Some folks, well, I have a quick and dirty FEM, here's some mode shapes. Be careful with that. Be very careful. You'll be wasting more time. You'll get answers, okay? But if the FEM is not the best quality possible, your elastic analyses are not going to be the best quality possible. So I can't stress that enough. I've dealt with that throughout many projects, many situations that you'd have to require and demand that you get the highest quality FEM possible. Otherwise, the solutions are going to be suspect, okay? We start usual equations. The structure is usual glorified mass spring dashpot systems, where the forcing function, so what you have is the system is the structural dynamic system. The forcing function is the unsteady aero. That's all it is. That's the basic setup, okay? Now, it's sometimes referred to as reduced order model, but it's not in the sense that you might have heard it, but when you have a structure, let's say you have a structure, if you have an FEM, you have an airplane, let's say it has 15,000 degrees of freedom, okay? You have an option. You can track the motions of all 15,000 degrees of freedom, or you can perform, like in Nastran, it's called solution 103. How many are familiar with solution 1, normal modes? That's called a normal modes analysis. Normal modes analysis, what it does is it decomposes the structural dynamic motion of 15,000 degrees of freedom into mode shapes. It's called the modal coordinates. So instead of 15,000, I might have 10 modes, where first bending, first torsion, second bending, now it looks like I'm doing breakdancing, but I'm not. Second bending, second torsion, symmetric, anti-symmetric mode shapes, okay? So you take 15,000 degrees of freedom, you break it down into 10 or 12 modes. So that's a reduction in the amount of mathematical complexity. That's why it's important to get mode shapes. So first, give me the best quality finite element possible. I need to be able to run solution 103 on it if it's Nastran, because that's going to give me my normal modes. Normal modes. You need the normal modes. If you don't have normal modes, you cannot do any elastic analysis, okay? Ground vibration test is when you have the hardware, you can do shaker, you shake it, you try to see what the modes are and the frequencies, and so you can compare them to your FEM. So GVT is really a ground test to validate your FEM. Right? So I won't spend a lot of time on that. This is more about the GVT. You can do vibration tests. Now, this is important. Let me spend a few minutes on this. In this diagram, I can cover how we perform CFD-based aeroelastic analysis, how we perform wind tunnel flutter testing, and how we perform flight flutter testing. All three of those can be covered with this chart. Right? And this is how it works. So you typically have Mach number versus dynamic pressure. And the goal in any aeroelastic analysis is to identify the most dangerous conditions. The most dangerous condition in aeroelastic analysis is flutter, because flutter results in an instability that destroys the structure. So that's the flutter boundary up there. Notice that as you go towards possibly increased compressibility, or if there is transonics, the transonic effects do tend to reduce stability. That's why transonics are so dangerous, because transonic flow reduces your flutter stability. Why is that? Anybody want to take a guess on that? What happens in transonic flow? Well, subsonic, when your wing moves, your aerodynamics responds almost immediately, and vice versa. It's good communication. Everything boils down to communication. Everything is good communication or bad communication, all right? Supersonics, likewise. There's different zones of communication. Transonics, what happens is you have a shock, and because of the nonlinearity of the shock, as the structure moves, there's a delay. The shock does not always respond immediately to the structure. So you start to get what's called a delay. Now, how many of you do systems analysis? Are delays usually good or bad? Delays are bad. Why is a delay bad? A delay is bad because it creates an unstable situation. It's like pilot-induced oscillations, right? I pull back on the stick, the airplane doesn't respond. Pull back more, responds too much. Then I have a delay, and I create instability. The same thing happens in aeroelasticity at transonic conditions. The shock, the nonlinearities, create a delay, a miscommunication, if you will, between the structural motion and the unsteady dynamic motion, so that they counteract each other, and they create a greater propensity for flutter behavior at a lower dynamic pressure. All right? So here's how it works. If I'm in the transonic dynamics tunnel, if I'm in the TDT, now the TDT, I can have different densities. All right? So let's say I start near a vacuum. I can pull out all the air of the TDT, I have a near vacuum, extremely low density. So I turn the fan on, so I increase the RPMs. If I increase the RPMs, I'm increasing velocity, right? So if I increase velocity, this is 1/2 rho v squared. So this Q goes up, and Mach number also goes up because velocity is going up. So I'm going along this line here. And this is how we test in the TDT. We increase the RPM. You see any flutter? And believe me, you're sitting there by the window watching this model bounce around. We suggested to have test engineers have their heart connected to a machine because you can see people's heart vibrate pretty bad. And it's very stressful. I've been there many times, and it's a very stressful situation. After a full day of flutter testing, I need like 15 hours of sleep. for real. So you come along this line, any flutter, no flutter, okay. You come back down, you bleed in some air. By bleeding air, you change the density, right? So now when you increase the RPM, your Q, you go along a different line. So your Q changes and your Mach obviously increases with velocity. So now you go up this line and you go up, you go up, you go up until you find flutter. And you see flutter in the TDT, you can punch out. We have something called a chicken switch. You punch out, opens up these bypass valves. The conditions of the test section drop very quickly, and you can sometimes pull away and save the model. I say sometimes because sometimes when you play with fire, you can't help but get burned. Sometimes the flutter is so strong and it shows up so quickly that even when you punch out, you can't get away from damaging the model. That happens. Okay? So you find a flutter point, you come back, you bleed in more air, you make these passes until you identify the flutter boundary. That's how we do it experimentally. Flight test, you can see you start at a maximum altitude, which is a low density. And you fly it, and no flutter, you come back, you come down in altitude. So flight test, you actually come down in altitude. Yeah?
How do you test for points past the bend there? So you see the bend for flutter?
Excellent.
Get there.
Ah, excellent. This is one of the dangers you have to be very careful with. One way we can do it is we can be at a certain Mach number, and what we do is, what do we do here? We bleed in. As you bleed in, while keeping a Mach number constant, you actually go up. Flutter, no flutter, no flutter, no flutter, no flutter. Now, here's the danger that you have to be careful about. This is what we call the backside. We have a name for it. It says when you're trying to find the backside, it's a dangerous maneuver. And I want you all to tell me why it's dangerous. We come up. All right, we find a flutter point, all right? We find a flutter point, what do? You can't back down. You can't pull air out fast enough, right, to move away from dangerous conditions. So what do you have to do? You have to punch out. You have to hit the chicken switch. But when you hit the chicken switch, you go along one of these paths. So if you're up here, you're up there, I hit the chicken switch, I'm going to go along this line. What do people see with that? What's the problem with that? I'm going to go from the pan into the fire. So when you're testing on the backside, it's extremely dangerous because if you do find flutter and you punch out, you're actually going back into one of the most dangerous conditions. And so we don't usually do that unless we feel we can get out of it safely somehow, because then you put yourself in a corner. Then you can't get out of it. Yeah.
Don't you just back off on the fan and try to come down the Mach number? I mean, I know you can't come down that fast.
No, you are at a constant Mach number.
Yeah, well, but can you slow down?
If you slow down, you go down this way because you change Mach and Q. See what I'm saying?
Yes.
That's the danger. So yeah, that's called the backside. That's a good point. Okay? And so CFD, we do the same thing. CFD, we pick a Mach number, and we pick a Mach number, and we look at Q1, look at Q2, Q3, Q4, until we see flutter. And so that's how we do it with CFD. And that's how we do a flight test, and that's how we do a TDT. Okay? All right, how about another real quick 5-minute break? And see you then.
How much longer did you
It's going to be till 11:30.
11:30?
Yeah.
Slides going to be available?
Yeah. Yeah, sure. Yeah. Just send me an email so I know who to send them to.
Can I get your email so we can send you an
Yeah, Walter. Walter.a.silva at nasa.gov. Yep. Hey, how's it going?
Good. You doing a talk right now?
Yeah.
Which one is it?
The elasticity. They said from 9 to 11:30.
9 to 11:30.
Yeah.
Okay. All right. I thought it was from 9 to 11. So.
It said a picture's worth 1,000 words. A video must be worth at least 10,000 words. So this is the A6 aircraft, which was an aircraft built by Grumman, who I worked for many years ago. This was the 86, tested in the Transatlantic Dynamics Tunnel in the TDT. And what you see was flutter, and it was unexpected and unpredicted. There is slow motion right there. You see the two modes combining? That's flutter. So the damage is real. The danger is real. It's not mathematics. It's not a nice textbook. This is real world structural damage that can occur.
How many sides does a pentagon have?
5.
Okay, all right. So let me continue now. So elasticity is aerodynamics, elastic forces, inertial forces. Turns out airplane designs had elastic problems from day one. Samuel Langley's monoplane had a problem in the Potomac. It was possibly aeroelastic divergence. Had it not been for that, history would be different nowadays. It wouldn't be the Wright brothers that had invented it. It would have been Samuel Langley who would have gotten credit for the first flight. Some terminology. There's two types of elastic phenomena, static and dynamic. So static is when the structure deforms and it sustains, keeps stable one way or another. Divergence is if you have forward swept wings, the wings want to bend back and they break off. That's divergence. That's bad. You don't want, anytime the wings come off, that's generally a bad thing, all right? So just keep that in mind. Dynamic, you have flutter, which you saw in the A6, buzz, and buffet. These are the equations for static, elastic divergence. The load and the structural restraint have to be equal. If the load exceeds the structural restraint, then the wing fails in divergence. These are the basic equations for flutter. You look at the mass, center of gravity. You see you have these two springs. This is called plunge and pitch. And those are the two basic modes for flutter, plunging and pitching. Those are the two simplest ways that you can model and analyze flutter. So flutter, what happens in flutter is that your bending and your torsion actually come together. What happens is the aerodynamics becomes the catalyst. The aerodynamics becomes the source that combines a plunging mode and a torsion mode, combines it into something like this. It's the aerodynamics, okay? And so here you have the bending and the torsion, and the aerodynamics, as you increase dynamic pressure, the aerodynamics, so here's the frequency of this one. Here's the frequency of this one. The aerodynamics increases the frequency of this one, decreases the frequency of this one, and they combine until you get flutter. So anytime you see what's called coalescence, frequencies coming together, that's bad, okay? Frequencies coalescing is bad. That means you're close to or at flutter, and that's what I mean, coalescence, okay? This is an example. there's something called these types of plots where you look at the frequency. If you see a mode go to 0 frequency, that's divergence. But if you see the modes coming together, that's flutter. One important thing you need to know about is called the VGF diagrams, V velocity, damping, and frequency diagrams. And this is classical aeroelasticity. This is the damping and frequency. So this is the damping. So let's say we have, here you have 4 modes. What you look for is 2 things. The damping, as you increase velocity, for example, you see the damping comes down this way. This is stable. As soon as one of these modes crosses the 0 line, that becomes unstable, all right? And what you see here is, you can see which 2 modes are coming together because these are the 2 frequencies. So both of these tell you something about what's happening. And you can have multiple things happening at the same time. You can have what's called a hump mode. It kind of goes up, goes unstable, becomes stable again. Or you have something that's called a hard crossing. The hard crossing is much more dangerous because you'll think, oh, look, it's stable, it's stable, it's stable. All of a sudden, boom, it's just going unstable very quickly. We call that a hard crossing. That's the more dangerous of the 2. But it can happen, and this is called a VGF plot. All right, so keep that in mind. This is classic aeroelastic. There's ways to alleviate flutter. I won't spend time on that. Some codes. Obviously, you want to know what codes are used for aeroelastic analysis. MSc Nastran, I talked about. How many of you here use Nastran? Raise your hands. When you use FEM, do you use Nastran? Well, that has an aeroelastic supplement typically, so you can do aeroelastic analysis with Nastran. CFL3D, Fun3D, and you got to look at all these solutions. Again, we talked about the modal. There's different methods of solving. If you're doing the frequency domain, you have to solve what's called determinant to find at which point the vehicle is going to go unstable, to find the condition. So again, I'm just giving you some terminology here. Now, there's something very important about choosing the number of modes. It's called, there's modal convergence. You got to have aerodynamic convergence and modal convergence as well. So here's a vehicle, and it's got 10 modes, okay? If I use only modes 1 and 3, I compute the flutter speed to be that, feet per second, and there's the flutter frequency. If I now do 2 and 3, I get that. If I use 1 through 3, notice it's changing. The flutter condition and the flutter frequency are changing as a function of the number of modes that I include, and this is very important. You can't just say, yeah, I did flutter analysis with the first 3 modes and it's safe. You can't do that. You have to look at 1 through 4, 1 through 5, 1 through 6, 1 through 7. And notice what happens. Beyond 1 through 7, it doesn't change. So you're converged. So that means that you need to include modes 1 through 7 to make sure you're capturing the full dynamics, the full aeroelastic response of the vehicle, because this is your correct flutter condition and that's your correct flutter frequency. Okay? So modal convergence is very, very important when you're considering this type of analysis. And here, again, is the VGF plot just showing what you're looking for. You're looking for the modes that cross into the upper part to see kind of what the problem is. And here, you see frequencies coming together and a frequency going to 0. That's divergence. Okay? All right, we'll show you this already. Let me say a few things now about aeroservoelasticity. So elasticity is the structure and the unsteady aero. Aeroservoelasticity is the structure, aerodynamics, and control systems. You might want to have, you have a control system. So there's 2 things. First, you want to make sure that adding the control system isn't going to deteriorate the performance of your vehicle, the aeroelastic. Why could that happen? Well, there's videos. You might look at ground resonance test. I forget which vehicle, but look up ground resonance test. You'll see something very dramatic. A ground resonance test is you take a vehicle, it's on the runway, it's not moving, it's not taxiing, it's just sitting there. And you turn the control system on. And then you just shake the structure. What happens is, if there's an instability in the aeroservoelastic system, the excitation you give to the structure triggers the control system instability. The control system then responds, which then triggers the structure, which then triggers, it goes into a positive feedback loop. And what you will see, and you see these videos, very dramatic, a helicopter or vehicle just boom, boom, bouncing dramatically and violently up and down until it gets pretty well damaged. That's ground resonance test, and that's called an adverse servo-elastic interaction. You got to be careful of those. But you might also use ASC to reduce the flutter. For example, if flutter happens at Mach 0.9, dynamic pressure of 100 psf, if you use active control system, you might be able to delay the flutter to maybe 120, 140, 150. So you can use active control systems to alter the aeroelastic behavior of the vehicle, right? Now, if you want to get into aeroelasticity, here's the things you want to know. And this is why I share all those things with you, because you want to know about aerodynamics, supersonic, transonic. You want to know about control systems, state space, Nyquist. You want to know about structural dynamics, mode shapes, frequencies, GVT, all right? So these are the types of things you need to study, make sure you understand it. You have rigid body modes, elastic modes. Sometimes one of the issues with some modern vehicles, if long supersonic vehicles, for example, or vehicles that are more span loaders, one of the things that happens is that you have rigid body modes, just plunging, for example, and elastic modes. Those can couple together. So you can have a vehicle that's flying along and it's unstable with flexibility while plunging and pitching. That's called body freedom flutter. Body freedom flutter, and it's a serious problem, and it's potentially a problem in some of the new configurations we're seeing. We're concerned about that in supersonic vehicles because they're very long, flexible fuselages whose rigid body modes, like short period, for example, are very close to the flexible modes, but span loaders tend to have same thing with longitudinal axes as well. Yeah.
There are two examples of that exactly on what you're talking about. The Voyager around the world airplane.
Yeah.
It was a span loader because the fuel was carried on its wings, and for the first several days, it had enough mass that either the short period or the fuel going coupled with the wing bending.
Yep.
And then there was a Helios high altitude solar power airplane,
Yep.
which was a flying wing, which also suffered. That was sort of a fugoid and wing flapping motion, which eventually destroyed.
That's right. That's right. So these are real issues, folks. And one important message for you all, the new generation. Many years ago, when we had conventional aircraft in industry, you could have one group working the flight controls. They worked the rigid body controls, and then you had the other group, loads and dynamics, which is what I was in, aeroelasticity. We could work the controls, the aeroelastic stuff. And then later, when the airplane's coming together, you put both together because there was enough separation between frequencies, between rigid body and elastic, that any possible coalescence was not feasible, it was not possible. As you all are coming along, vehicles are changing. You have new concepts. You have concepts that are supersonic, that are long and flexible. You have span loaders. You're pushing the boundaries of aeroelasticity and aeroelasticity, and my advice to you is do not treat these separately. Do not encourage, or maybe you should discourage or encourage that anybody who's doing control system, they're going to say, oh, it's just for the rigid body part. Get them into the conversation early on when you're doing your aeroelastic analysis, because if you try and bring these things together, once the airplane is built, that's bad news. You may have problems that are too expensive to solve. So we used to do it old school, was separate. You guys are new school. You guys are the new generation. Don't do that. Please make sure you get everybody integrated early on. Right? That's probably the biggest message I can give you. This is what I'm talking about right here. High-speed civil transport. You have closely coupled rigid body and flexible modes. So you get body freedom flutters, a very real possibility with these vehicles. And these could be the vehicles of the future that we'll see. And you all might be working on them out in industry somewhere at some point. So keep this in mind, all right? If nothing else, bring all these folks. These are kind of the stuff we look at, the aerodynamic paneling, the mode shapes, stability, root locus plots. And here's just the basic way to think about elasticity is a feedback mechanism between your structure and your dynamics, right? Even with CFD. So your structure deforms, the CFD computes the pressures, then you integrate the pressures into a force. That force then gets fed back into the structure. The structure has some stiffness, some damping. The structure responds with its own motion due to that force. It comes back to the CFD. You compute new pressures, new forces. And so what you have really, the simplest way to think about elasticity is a feedback mechanism between your structure and your aerodynamics, okay? And I'm going to just skip through a whole bunch of these things here. Get to some other, again, there's a lot here, and it's not my intent to walk you through all this. But if you're going to go into control systems, actuators are very important. Typically, when folks do an aeroelastic analysis, what they're looking at is they're using what's called ideal actuators. Ideal means their frequency content is perfect, so they don't filter anything out. But you need to include real models of real actuators. So when you start doing control systems, the actuators have to be real. The sensors have their own frequency issues. So all this says is you're going to have to start including more real-world effects. Won't worry about gust. Now, one thing that is important in aeroelasticity is because it's going to be used with control systems, an aeroelastic math model consists of an A, B, C, D matrix. So an aeroelastic math model consists of a state space equations that include the entire aeroelastic system and the control system. That's why I cover state space equations, because an ASE math model consists of state space equations, and you use that to design a control system. So when you bring a ABCD matrix into MATLAB, you can then design a control system for that aeroelastic system. Okay? So that's why we cover all that. There's different methods. Something called ISAC, which is a tool we developed many years ago, which is linear. I won't spend a lot of time on that. These show you the flow chart of information. This is important. Keep in mind that any math model you have is approximate. There's unmodeled quantities and there's uncertainties that you have to be aware of. Just remember that everything that you do is an approximation. Mathematics is an approximation of the physics. It's not exact. And if you always keep that in mind, you will make wise decisions as to what you're doing. Okay? And lastly, let me just show you kind of a, let's see, a root locus. Where's another one? For example, this is something that flutter suppression might do for you. This is an aeroelastic system. So if you have a flutter suppression system, it's off. This is the root locus. Here's mode 1, mode 2. This is what it looks like in root locus. This is coalescence. And as soon as this mode crosses the imaginary axis, that's flutter right there. So you can actually design a control system with using ASE methods that will then alter the response of the vehicle, and you can delay the flutter. So the flutter won't happen at this Q. It could happen at 20% higher Q. And that's what flutter suppression does. Likewise, you can do gust load alleviation to reduce the loads on the gust that a gust imposes on a wing. You can do ride quality control. So aeroelasticity is a way to incorporate control systems as a way to alter, modify, or change the aeroelastic response. Okay? And I think I'll stop here. Any questions? Thanks a lot for your attention. I really appreciate it. There's a lot here, so hopefully I covered some of the main goals. So thanks a lot. Appreciate it. We have about 5 minutes. Any questions, comments, concerns, queries?
You mentioned that that the analysis is just an approximation of the physics. You may also mention that testing is an approximation of subscale testing is an approximation.
Yeah, testing is not by any means the answer either. They both have their issues, and it's good to be aware of all the issues.
Analysis will give you, the testing will give you the wrong answer to 3 decimal places, and then the CFD will give you the wrong answer to 16 decimal places.
There you go. I like that. Thanks. Thanks. See you. Any questions for anybody? All right. Well, thanks a lot. Send me an email if you'd like to get a copy of the notes. And good luck to all of you. Your summer. Enjoy your time here. If you have any questions or anything on this, feel free to send me an email anytime if you have any questions on it. All right. Take it easy. Thanks a lot.